Uh-huh. Hello. So we will start the second lecture on HAR. And today Pei will talk about concept-centered representation. And
what is today?
Yes. I think that's right. Great.
Thanks for coming and start on time. Last week in the first lecture, I think I have explained what we want to do. That is according to our understanding about intelligence. We want to build an adaptive system which can work in a realistic environment. By that, we mean the system can deal with insufficient knowledge and resource and try to adapt to according to its experience. So today we will go into design detail. Start from knowledge representation. That's very often where AI system design starts. So what we use is called a concept-centered representation, which I'll explain. So first, the big picture. When you describe a system in this context, what you're supposed to do. According to my framework of analyze, actually this is also shared by many people. The most important components in this context, or what we call information processing system, consists of three major components. The first one very often is called goal. Sometimes you also call the motivation or drive or task or problem. Of course, the words are all different. It's more or less a different flavor, but their difference here we can ignore. Okay. Anyway, this is what the system want to do or want to maintain, want to achieve, whatever. And the second part is the other end. That's what the system can do, which can be called actions, can be called operation, behavior, or solution. So what you want and what you can do. And then the third one is the relation between them, which is typically called knowledge. Okay. So the knowledge tells you if you do this, you can get that. So it's relating your ability to your purpose. That's another way to put it. And also it can be called beliefs, or also related to skills, programs in computer, and so on. So to me, that's the three major components, which we are going to analyze into detail in the future. And also, another perspective of description is the language you use. To me, in this context, you typically describe your system as three different languages or three different levels of description. First, you typically start with some kind of theory. In this case, it's a theory about intelligence, according to what you think intelligence is, how it works, and so on. This is typically described in a human language, or what we call natural language. For now, we're describing that in English. Right? And then the second level is you typically need a formal model, or a model, whatever you call it, in a formal language. Here is you can also call it a symbolic language or a mathematical language. And finally, for the purpose of AI, eventually you need to build it. Okay. Meaning that if it's a pure software implementation, then it will be described in software in program language. If it's a software hardware combination, you also need to have a device, right? Which we just, in general, we just say, okay, you need this, some kind of computer language or more than one. So if you think about these three layers, you can see that the top layer and the bottom layer is obvious, right? Clearly, you need to have some idea in your mind, and eventually you need to build something. And the one that deserves more discussion is the one in the middle. That is whether you do or do not need a formal representation of your theory or of your system. Actually, currently in the current AGI research, there are some people who don't think it's necessary. They have some idea, then they begin to write code. Okay? But most people, I think, believe there is a need to introduce an intermediate step by building a formal model. The major purpose, I think, is to compare with the other two. See, the problem about natural language description is the ambiguity. We know that in natural language, no matter which language, almost every word can be interpreted in multiple ways, and that causes a lot of trouble. So the purpose of using a formal language, I think, primarily is to make your theory accurate and clear. No, as reduce ambiguity as much as you can. Okay. On the other hand, why, if that's the case, why not just directly write code, which is also accurate? Because formal models tend to be more abstract than the concrete computer implementation. This gives you the flexibility. Especially we know that the same design typically have more than one possible implementation. So if you have an intermediate model, a level of description, which saves you from all the technical details. Okay. I mention this because also this applies to this course. In the following, most of my discussion will be at this intermediate level. Of course, I still use English, but the content will be more using mathematical formula or symbolic representation with natural language to explain, and also sometimes we talk about the computer implementation. But the focus will be in the middle level. So, but if that's the case, then that raises the issue: which language do you want to use? You see, here is what I see as the three most important traditions currently in the field of formalization or symbolization. Okay. The first one actually starts from physics. That's sometimes called the dynamic system tradition, which currently is mostly used in, for example, almost all neural networks are described in this way. This language basically see the object you want to describe as can be measured by a whole bunch of numerical measurements. So all the values of those measurements represent that object at a certain moment, and which can be seen as a point in a multidimensional space. I assume you're all familiar with that. And then any change in that object corresponds to some kind of function which describe how that point moves in that multidimensional space. And also the functions that map one space to another. That's how we usually describe a neural network and many other similar systems. So this is basically a physics tradition. A second one is a tradition mostly from symbolic logic. Here, the current situation of a system is described by a bunch of sentences in a certain language. Here is a formal language, it's not a human natural language anymore. It's accurately defined grammar rules. Then the activity of the system is described by a bunch of inference rules, which derive new sentence from existing sentence. That also you're familiar with. So that's the logical tradition. And finally is the computer science tradition. You know this computer science is nothing but data structure plus algorithm, right? So that your object is described by the value of the data structure, then the algorithm will work on the data structure, make change and so on. So eventually, almost all the implementations will be mapped there. So which one is better? Well, it depends on who you ask, right? So my conclusion is first, I think it can be argued that in principle, they're equivalent. So whatever can be done in one language can be done in the other. But on the other hand, for a given specific task, they're not equivalent. Some of them are easier than some others. So here, a metaphor is like the debate, I think you know about which is the best program language, right? On one hand, they're all the same. Whatever you can do with one, you can do with the other. But on the other hand, of course, that's not the case if we're talking about practical application. Okay, some language is much easier for certain type of job. So here, I think it's the same thing. Why I want to raise this? Because our work in the following, is designed in the framework of the logic tradition, okay, which was a popular idea in AI, but currently not at all. Okay. Many people will ask you why you want to describe your system as a reasoning system, which, in AI is already dead. Okay, we have a reason to do that, which I will explain. But first, I will just set up the framework so we know there are other options, and we pick this one for a reason. So what is called the reasoning system? This one is not too controversial. Typically, we say a reasoning system in this context when we're talking about AI. Roughly speaking, there are two parts. One is the so-called logic part, which is a logic in the traditional sense, which typically consists of three major components. First, I already mentioned a language, a formal or semi-formal language. You need to specify what kind of sentence is allowed in this to represent your knowledge. And the second one, this one everyone knows, is a set of inference rules, which are related to the first one because it's only use those sentences to do reasoning. Finally, there is a third part, very often ignored by people, because this one is kind of like invisible. It's a semantics. It's a theory which explains to you how to use that language or what that language means, each symbol in that language. Okay, so it's about meaning. You need to know that, otherwise a symbolic language makes no sense. And the second part is truth. This is used to justify your inference rules. Your reasoning system, inference rules is not any arbitrary rule. Okay, you must give it a reason. So you can call it logic. Traditionally, inference rule is justified by being valid in the sense that it's truth preserving. Right? You can get truth from truth. So because of that, it's logic. So that's what we usually mean by logic. But when we're talking about reasoning system in the AI context, it's more than that. This is usually just on paper or in book. Okay? And in the AI part, you need to implement it in a computer system, which we typically call it to add a control part into it, even though it's not completely about control only. First, you need a memory structure. You need to actually put all the inference rules, all the grammar rules, as well as all the sentence you take and the problem you want to solve, all of them, you need to organize it somehow into your memory. So it's a memory structure, or you can call it a knowledge structure, or you can call it data structure. They're all related concepts. But you need to serve this purpose. And also, there is a mechanism, this is typically called the control, which decide in each step which rule to use. you see that each inference rule, you already specify only one step of your problem solving process. Okay, it's kind of like from A and B, you can derive C, something like that. Okay, so for a given problem, typically you cannot solve it in one step in most of the case. So what you need to do is to decide, I do this step, then I do that step, and so on. You build a chain of inference steps, which will eventually give you your final result. Here, the problem is very often at any moment, the applicable rule is not unique. It's kind of like you can go in this direction, you can go in this direction. Okay, logic only tell you in each step what you're supposed to do. But how to combine those steps into a complete process, that's the job of the control mechanism. Okay, which is quite tricky, which actually we are going to discuss mostly next week. Okay. Or the week after next week, actually. So now I can explain. So given my understanding of reasoning system, as I just specified, why I think this is a better framework compared to the more popular one, like vector space, or directly talk about data structure. I think there are several major advantages from AI, especially from AGI's point of view. First one is a relatively clear separation between the meta-level knowledge and the object-level knowledge. Okay, this terminology comes, from language study, and in this context, what we call object-level knowledge is the content of your memory. For example, you want to describe this room so that your knowledge will include the people and the tables and chairs, their location, and so on. They're all object level. Meta level, on the other hand, is talking about how to process the object level knowledge. Actually, what I just said in the previous slide, they're all meta level things, like say grammar rule, like inference rule, control mechanism, and so on. Okay. And that part is clearly separated from the content of your knowledge. Or you can say one is the content, the other one is the mechanism you use to manipulate or to process the content. And the same separation can be done in other representation framework, but it's more clear in the logic framework. And later we'll see this distinction matters a lot in our design. And I can tell you why. It's because later you will see that the meta-level knowledge in our system is completely fixed. It's completely determined by the designer. Object level, everything can change. Everything comes from the system's own experience. It's learned. Okay, that separation is very clear in this paradigm. And also the separation between logic and control, which I already said, that's also very crucial. Okay. For example, if you do computer science paradigm, the logic part and the control part are mixed together into an algorithm, which for the AGI purpose actually is a big problem, which I will explain later. Okay. So again here, this separation will allow you to use a fixed logic with a flexible control. We can use a metaphor of building block. Okay, the logic will decide what building block you have. The control part will decide how to put those blocks together for each scenario. And you don't change the blocks, you change the way they're put together. So in the logic framework, in the reasoning system framework, this is relatively clear, which we will see more. And the third one is really tied to the goal of AGI. You see, this framework is by nature is general purpose. You don't have a logic for physics, a logic for chemistry, and another logic for biology. You only have one logic. Okay, meaning what? Meaning the formal language, the inference rules, and the semantics are independent to the domain, which is very often not the case if you use the other two. Okay? If you use a vector representation, you need to decide at the very beginning what each of the dimension in that vector means, which is very often context sensitive. Okay? You change from one context to another, you need to change the meaning of those dimensions. And also data structure and algorithm design also have a similar issue. But the logic, well, of course, what I'm saying is always a matter of degree, okay? Because I already told you, in principle, you can translate one to the other. But still, there is a relative naturalness in the logic framework to do domain-independent design. And also, this is a big topic, hot topic in recent years, right? Explainability and justifiability. Also, in this aspect, the logic reasoning system has a big advantage compared to the others. Now, all the problem come, actually from deep learning, right? It's very powerful, but you don't understand it. A reasoning system, if you want to understand it, you first need to understand the semantics, then, which will give you justification for the rules. And there's still issues, but relatively little. So that's the major reason, actually, for us to pick this paradigm. But of course, on the other hand, there are big issues. That's why this is not popular, right? In the current AI. Even within AGI, not many people are doing reasoning systems. Why? Well, we understand that. First is the association with the traditional so-called symbolic AI tradition. Okay. Wherever we tell other people we're doing AGI in the framework of a reasoning system, people will say, oh, no, it's dead already. Okay, there's no way for that to work. And this is not a new idea, and it doesn't work. It used to be very popular, okay, even dominating the AI research to a certain degree. But it's not successful. To the extent that people learn the conclusion that it is not going to work. So that's something we need to answer. And that actually comes from a source. The so-called symbolic AI theoretically is from mathematical logic with some variation to make it work in computer systems. Okay. And the mathematical logic is great, of course. It has made a lot of great success and great theoretical and practical contributions, but we only need to mention one thing. Okay, if you still remember what I said last week, our theoretical foundation is based on the assumption of insufficient knowledge and resource, where mathematical logic assumes exactly the opposite. You see, in an axiomatic reasoning system, which is mathematical logic is designed to use for, all the knowledge in principle are in the axioms and the inference rules. It's already there. Okay? You only need to figure out its implications or conclusions. All the knowledge are there. You don't have the issue of, oh, there is a new discovery, like in empirical science. In math, there is no such a thing. Okay? Everything is already given. Second, in mathematical reasoning, you completely ignore the cause of time and space. Okay, if a proof would take 1,000 steps to finish, well, just do it. Okay? It doesn't make it less valuable than another proof which only takes 3 steps, even though we humans like the other one. but it doesn't make the first one worse from a mathematical point of view. They don't care about space at the time. Okay. So in a sense, we are actually fighting in the backyard of the enemy, right? So we're using mathematical logic in some sense, but we are trying to completely change its fundamentals. Well, how can that happen? So you'll see that the first issue, actually this is a central issue of today's discussion, is mathematical logic is based on the assumption, okay, you can call this conclusion logical because it's derived according to solid or valid inference rules from solid or true premise. Now, as I said last week, we assume insufficient knowledge and resource, or so-called AIKR assumption, which basically means you don't have absolute truth to start with, which also means you don't have inference rules which are valid in the traditional sense. You cannot do from truth to truth inference anymore. So you see, this is actually the reason, exact reason why many people leave this field or think this is dead end for AI. Because if you don't have anything which is logically justifiable, then your conclusion just sounds like arbitrary. It's kind of like everything goes. If you cannot prove your conclusion is true, how can you say it's better than the others? So that's how we are going to handle that theoretical challenge. First, that's what I'm going to explain. Then we can talk about how to actually do it in a computer. But this clearly you can see is first is a theoretical or philosophical problem. So I already, last week, I think I have already suggested the direction we are moving. That is, we are going to do something based on the concept of adaptation. Adaptation does not guarantee success. Okay, you learn from your past experience, but you may learn it wrong. But no matter what, it's better than not to learn from it at all. Okay. So that's the intuitive idea toward the previous challenge. So how to actually do that? Here, the key concept is concept. Okay. So adaptation means that you need to learn from your experience, but the experience itself is quite complicated and messy. In this discussion, what we call experience is just simply the history of interaction between the system and its environment. Okay. And it's have some sensor, some actuator, and you see something and do something, and all that history put together, roughly speaking, that's a system's experience. We are using this word in a very, very naive and simple way. So what is a concept? Okay, and here we are begin to be different. Our opinion about experience is not that special. Our opinion about concept is very different from the current mainstream conception, especially compared to traditional symbolic AI. Think about it. According to symbolic AI, intuitively speaking, what is the concept of, for example, chair? Well, people will say, without all the details or accurate definition, roughly speaking, you have a lot of chairs, like, for example, in this room, which forms a set, right? And chair, the word chair is just a name which associated to that set. But in our system, A concept is abstraction of segments of experience. That is, first experience is a stream of interactions, and then you turn it into concept. Roughly speaking, goes through two major operations. One is segmentation. You cut it into sections because the whole experience is too long, right? It's actually, you can say it's infinitely long on both directions. Well, not really infinite, but too long for you to actually to take the whole into consideration. You need to cut a section of it. And also abstract, meaning that you don't keep all the details. Okay, you keep some feature of that segment, and the result is what we call a concept. So we're using concept, later you will see, in a much more broad sense compared to the traditional usage. It doesn't have to have a well-defined boundary or something like that. It doesn't have to refer to objects that actually exist in the outside world. None of those are required. It's possible, but not required. So see, the come from experience is after segmentation and abstraction, and also every concept has an internal name within the system. So it can be recognized by the system and can be manipulated. It can be the object of the thinking process. And you can process it. And here, this name doesn't have to correspond to any word in human language or any language. Okay? It's an internal name. That's why I call it the identifier later. So that's what we call a concept. So why we need a concept? Actually, this directly comes from my working definition of intelligence. You see, this is a way to make experience manageable. And also, this provides a bridge between the past, the present, and the future. Last week, I already stressed this. Okay? According to my working definition of the system of intelligence, the intelligent system must be open to new experience, meaning that we do not assume the future is the same as the past. Actually, we can go to the other extreme to say that the future is clearly not the same as the past. Or in other words, you can say that, accurately speaking, the future is unknown. And the future gradually will become the past, right? The past become the present first, then become the past. So when we are dealing with the current situation, in principle, this is a situation we never seen before. So how can we still deal with it? Well, if you do segmentation and abstraction, you get something which is the same as because you are not keeping all the details into consideration. Actually, for example, each of us is not the same person as the person in the last week, right? We have changed. But we will say, oh, well, as far as this discussion goes, I don't care about your change in a week. Well, I will treat you as the same person as the one I met last week. You see, you have to go through concept for that to happen. Otherwise, you will have to say they're different. And actually, this abstraction and segmentation sometimes will cause problem, will cause mistake. We all know that. But still, you see, concept will allow us to apply past experience into new situations by ignoring some details. Also, this is for the previous point is for insufficient knowledge. Right? What if you don't know the current? And the second part is about insufficient resource. A concept provides a summary or compressed form of experience because you ignore a lot of detail. Okay? only when you're doing that, you can handle it. You can handle your experience with your available knowledge resources. Otherwise, you don't have the time and space. Okay, this point is easier to understand. So now we see that in this system, knowledge is nothing but conceptual relations. So again, concept is part of experience, and they're related to each other that give you knowledge, which may sound obvious and uncontroversial, but compare it to another version. You see, what is the most common version of or notion of knowledge?
Sorry, can you repeat the question?
In my theory, knowledge is nothing but conceptual relations. But that's different from, for example, if you check knowledge in AI testing, they typically tell you knowledge is a description about the world as it is, or hopefully. Okay? And there is a fundamental difference between these two.
Well, one that comes to mind is that your way of defining knowledge as relations is a bit like talking about functions and morphisms and things like that, as opposed to the traditional one, which would be just statements or like objects or like fixed things.
That's one part of it. Another more important part, we can say that in my definition, I'm suggesting the subjective nature of knowledge. And in the traditional definition, they suggest the objective nature of knowledge. Okay. In a sense, you can say, oh, I can see the point, but I will say it's both. You know, it cannot be purely subjective, otherwise, blah, 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 blah. Yeah, of course, we know that. Okay, I will explain that later. Okay. But here you can see that our definition is just basically say that what you call knowledge is nothing but a summary of your own experience, to start with, at least. So here is where the trouble starts. You see, according to my definition or working definition I just explained, even I gave you the same experience as a stream of input and output, sensation and actions, interaction, blah, 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 blah. If you want to cut it and abstract from it so that you get a concept level description of the experience, there is no unique solution. You can cut it in many different places, and you can abstract it by ignoring different details. It still satisfies what I said. Yes. That to me is actually the starting point why we have different opinions, even if we live in the same world. Okay. Later we will see that is a fundamental difference is we conceptualize our experience differently. Okay, that causes a lot of trouble, but that in a sense or to a certain degree is inevitable. That's why I suggest to start from a subjective point of view. Later we will talk about where objectivity comes from. So there is no correct way to talk about the world or talk about the experience. Okay, there are different ways. Each of them has its advantage and disadvantage and so on. So anyway, that's what I assumed. Later we will see what it implies. So now it means what? It means it leads to another thing. This is highly controversial. What is the meaning of a concept? We know it's a tricky point, not only in philosophy, it's also a tricky point in AI as well as in psychology or in linguistics, and even in our daily life. Okay, what do we mean by that, right? Very often for the same concept, we have different opinions. A typical example is what's the meaning of intelligence, which last week I spent more than an hour to talk about. So how the meaning of a concept is designed. Again, traditional opinion, I think you're familiar with. There are two approaches. One is use reference or connotation, some whatever you call it. It's basically say a word is the label of an object outside there, just like my previous example of chairs. Okay. So what's the meaning of the word chair? Well, that's the set of chairs that exist in the world. So that's the reference. Another common approach is definition. Okay. You define the meaning of a word, a concept using other concepts. And these two are very often combined together, say that the basic concept get its meaning by refer to objects or events in the world. More complicated concepts get their meaning using the simple ones with definition. But my approach take a very different point of view, which is continuous from the previous discussion. What a concept means to a system at a certain moment depends on the experience it corresponds to that system at that time. Okay. So the meaning of a concept is in its experience relation with other concepts, not according to a definition or a reference to the outside world. To be more specific, what kind of relation we're talking about? Well, several of them later we will see. We can start with, for example, temporal relation, spatial relation. This is especially related to sensory motor. And also abstraction relation. One concept maybe is an abstraction of another one. So now in the system, each concept has an internal identifier, which I already mentioned. Okay. So in this sense, you can say that that identifier or that name is a symbol that represents this concept. Okay. So in that sense, you can still say, oh, your system is a symbolic system. You can put it that way. But it's not symbolic in the traditional sense. In the traditional sense, what they say is, they say every concept is a symbol of something in the outside world. Okay, that's completely different from our position. So I use two simple diagrams or a figure to show you the difference between these two opinions or two types of semantics. So this is more like the traditional, accurately speaking, is called model theoretic semantics. Okay. And here the model is not a computer model. The model is your description about the world. Okay. Like for example, in this case, in your mind, you have this sentence say that the floor is in the pot. So here, the basic assumption is in the outside world, there is a thing that called a floor. And here we ignore all the details, okay? There is another thing called pot, and the relation is what we call something in something else, that in relation, okay? So what do you have in your mind? Each of them you see refers to an outside object, relation, property, event, which give you the meaning of that concept or symbol. Okay, so this pot is a symbol that represents an object in outside world. This is the semantics that I'm suggesting, which later we'll see is called experience-grounded semantics. Okay. Of course, I also acknowledge there is outside world. Of course, I'm not saying everything is our own imagination or something like that, or illusion. But you don't have a well-defined objects. What do you call an object or event or that kind of thing? That's your own conceptualization of your experience. Okay, so instead of have a clear-cut object relations, you have a whole bunch of things in your mind. And each of them in my theory is called a concept, okay, which you can say it represents something. It represents part of the system's experience. So if in that sense you call it a symbol, it's okay. But it's not the symbol in the traditional sense, because none of them correspond to this or this. You see, we do not even assume there is a well-defined ontology, meaning that what is out there, how they're related to each other, or there is an objective, accurate, correct, complete description about the environment. We do not assume that, even though the traditional model assume that. Basically say that what you have in your mind are just labels or symbols of the thing, you know. And this is a very, very, very fundamental difference, not just pure philosophy. And later you will see all the technical difference come from this, this different treatment. For example, I guess many of you are familiar with this Chinese room argument and the symbol grounding problem. Okay, we don't have the time for detail, but this exactly the problem of this picture, of the traditional picture. You see, if your concepts just refers to objects in the world, how do you know which one related to which one? How do you know that? Okay, and that's, to me, that's the core of the Chinese room argument issue. And the symbol grounding is a proposed solution to that, say that, okay, you need to ground your symbol to what? To your sensory motor experience. For example, you should know that a floor corresponds to a certain type of perception, so that the meaning of floor is nothing but that perception, okay? To me, it's have some similarity with my treatment, but I don't completely agree with it. Okay, I don't think the meaning of concepts can be completely grounded in direct sensory motor experience. So, you know, for example, how about abstract concepts? Okay, you don't have anything that can give you the grounding of that. Anyway, we don't have the time for that. And on the other hand, of course, I'm not claiming this is completely my own idea. My position on this aspect is actually closer to Piaget's theory about assimilation and accommodation. Again, I assume many of you are familiar with that. And this opinions basically say that you're using your existing concept to organize your perception. You kind of, to put it in extreme, you only see the things that you understand. Okay, because you can use your existing concept to capture a new experience. But on the other hand, where are the concepts come from? Right? The experience at the same time also is going to build and also change your concepts. That's the accommodation part. Okay, the assimilation part, it means that you use your existing concept to organize, to perceive the world. I think that's a much better description about this perception process and also meaning, where meaning come from, than the symbol grounding. So that said, this become to move into the technical part. The memory of our system is, roughly speaking, it's just a conceptual network, as you can see. Okay, every concept has a name, which is called a term in our system. And but there are many different types of terms. Some of the terms may correspond to a sensation. Some of them may correspond to an operation. Some of them may correspond to a word in a natural language, but not all of them. Okay, there are many, actually most of the concepts, you don't have a way to express it to someone else. But you know it yourself, you can identify it. And also there's a whole bunch of things called internal concepts. That's more like what I just said. Okay, and also very important, they're compounds. You use them to combine them in a certain way to build a more complicated ones. Okay? And this is also a topic we are going to go in detail in the future. So the difference is here, everything start from experience, but all of them are abstractions. It's just different degree. Okay? You can see according to my drawing, kind of like experience is here below everything. Then when you're moving up, you become more and more abstract. And another thing that related to the traditional AI debate is there is no such a thing as so-called symbol versus sub-symbol distinction. Okay? According to traditional, or now, not only traditional, now still many people believe it. Say, for example, they say neural network is good for sub-symbolic materials, and the traditional logic and so on are better for symbolic logic. Well, for symbolic processing, blah, 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 blah. In this picture, actually, there's no such a distinction. Everything is abstract to a degree, and what we call symbolic tend to be the one that with a higher level of abstraction. What we call sub-symbolic tend to have a lower level of abstraction, but there's no fundamental difference. Okay? We don't draw a line, say that, so you do a hybrid or something. So like, for example, this kind of drawing, this kind of picture is already an abstraction from your actual. So it's more like a continuous than a discrete separation of it. And we will see more about it. And also about the links, we will see more about that later. Now, another big topic in semantics. So what we just said is about meaning. The second one is about truth. Okay. We all know the intuitive meaning of truth. That is, your opinion agree with the reality, right? If I say there are chairs in the room, that's true because there are chairs in the room. If I say there is an elephant in the room, that's false because as far as we can tell, there's no elephant in the room. So that's the traditional concept of truth, which is very, very attractive. It makes a lot of sense. But that's not the one we're taking in this theory. Instead, as the title tells you, truth value here is not a measurement that compare a statement with the reality. Instead, it's once again, is a comparison between a statement and your own experience. Your experience, of course, comes from your interaction with the outside world, but it's not the outside world. It's different. Okay? You see, as I said, knowledge summarizes experience abstractly, so it's inevitably uncertain. Why? Because, as I said, it's basically what we call a concept is also what people usually call a pattern, right? What do you get in your experience? You selectively keep some information, and you say, okay, I see a certain pattern. But that pattern maybe is true at a certain moment, but at another moment, it may be no longer the case anymore. So very often they say it's uncertain. First, it's very often because the same pattern or same regularity you summarize from experience agree with part of experience, but disagree with another part. So that's where uncertainty comes from in the first place. The second point, even if it's completely agree with all of your experience, there is still something called the future, right? we cannot assume the future will be the same as the past. So you can never be absolutely certain about anything at the object level. That's the position taken in this data. Okay. That also go back to that assumption of insufficient knowledge and resource, which I already mentioned. Everything you believe can be wrong when you check against future situations. Okay. If I just say that, people will say, yeah, I think that makes sense. But still, something is more certain than something else. And you cannot just say, oh, because everything is uncertain, then everything goes. Clearly, you cannot take that position. Okay. So you'll see that the truth value in our system is the system's degree of belief, which compare this thing, this statement, or whatever you're talking about, with the available evidence. Which may sound actually, in today's world, I think with the machine learning so popular, many people may say, oh, I think that's the case. But if you check the history, this is completely different from the traditional definition. So if a statement represents a conceptual relation, as I said, okay, which can be experienced repeatedly, of course, otherwise it will not match relate the past and the future, right? So we always want something which is general enough, not just talking about one case in history. It can also be used for the current and for the future. Then what? Then you run into the issue I mentioned. So we will start from the simplest case. We just assume in the simplest regularized situation, we can test a statement and the result is either true or false. And it will either agree with something or disagree with something in yours. But of course, in the future, we will talk about partial agreement and so on. But we will start from idealized situation. So if that is the case, we have something which can be repeatedly tested, and each time it will either be true or false. Then from there, what you can say? We can use that as the foundation of our measurement of uncertainty in the system. So first, you'll see that in that situation, I can simply count how many success and how many failures I have, right? That's very intuitive. That's what we are doing in our daily life. In this system, it's called the amount of positive and negative evidence, respectively. And we use this W plus and W minus to indicate those numbers. It's kind of like, yeah, I have a hypothesis, I test it 10 times, and 6 times it works, 4 times it fails, something like that. Everyone is familiar with that. Then the first measurement we introduce is what we call frequency, which is the proportion of positive evidence among all evidence. All evidence means positive plus negative. Okay, like in my previous example, 10 times 6 success, 4 failure, then it's 0.6. Right? And you will say this is too simple, right? Yeah. We have a second one. And this one is unique to this system. It's different from everyone else. Even though this one is also super simple. What we call confidence is not the same as the so-called confidence interval in statistics, even though it captures the same similar intuition. Okay, you see, first the frequency. Some people may say, oh, this is just probability. No, it's not. Probability is the limit of this ratio, right? And here, limit means what? Limit can only be obtained in the infinite future, which of course, according to my philosophy, that's illegal. You don't know the infinite future. You only know what you know. Okay, so this value clearly, as the system get more and more experience, this value is going to change from time to time. But it still share the same intuition with probability. 100% true, 20% true, of course, that's different level of uncertainty. But if we say 20% true, that means, does that mean 2 out of 10 or 200 of 1,000? Will they give you the same ratio? But clearly we know that's different scenario. And that difference is captured by the second number. You see, this is W divided by, W is the total number of evidence, or it's kind of like how many tests you have done, divided by W plus K, where K is the system parameter, which can be anything larger than 1. Okay, what that's supposed to mean? Here, the intuitive idea also is actually very simple. There is another uncertainty which captures the first one. The frequency actually captures the relative ratio of positive versus negative. That's very clear. The second one captures which intuition? Captures the intuition about how much you know about this. Okay, no matter whether it's positive or negative. You can see the formula, and this K is a constant. When W equal to 0, confidence is 0. When W is increasing, this C will increase monotonically. Eventually, it will convert to 1, but it will never reach 1 because this is always larger than this by a little bit. Okay? So this is a technical explanation about what I said. The system is never absolutely sure about its conclusion. We are talking about this confidence level. Frequency, on the other hand, can be 100%. And also can be 0. You can take that extreme case. Okay. Confidence will never reach its upper bound, but it can approximate. It's kind of like the more you know, the more sure you are about your belief, even though you still can be wrong. Okay? Because this just measure what you know, it does not assume anything about the future. And what is this K? This is what we call a personal parameter, a personality parameter. Actually, what we are doing here, you see this formula is very similar to this formula in the sense that this is positive compared to total. Total is positive plus negative. Okay? This is what? This is what you know compared to what you don't know yet. This is not a new idea. Many people talk about, for example, talk about second order probability. A probability itself can be uncertain. So we can talk about how true it is. But the trouble about this picture is future is infinite. Okay? No matter how much you have already known, compared to infinite, you're there. So that's an issue that many people have already realized that they think this is not going to work. So what I'm talking about here is I always compare what you know to a finite future. The simplest case, actually, that's the default we have been using. We take K equal to 1. What does that mean in this case? Compare to the next testing. What do you already know? If you already tested twice, compared to the next one, it's 2 to 1. Okay? If you already tested 1 million times, compared to the next one, it's 1 million to 1. In the second scenario, you see that 1 doesn't really matter much, but in the first scenario, it matters a lot. So this one actually measures intuitively how much you may change your belief in the future. So high confidence doesn't mean it's closer to the reality. It means you're unlikely to change, or you're unlikely to change much because you already know a lot with respect to the same amount of future evidence. That's what this K measures. So we have another one. We can talk about the frequency interval. That is, this frequency in the near future. Here, near future is defined by this K, the coming of amount of new evidence of this much. And we see clearly if the current frequency is this, if all new evidence are negative, okay, so the total is increased by this amount, the positive amount remains the same. So that's one extreme. The other extreme is all the coming evidence in the near future are positive, which will make this one, all both increase by K. So everything else are in between. Okay. So if your current frequency is here, I know in the near future your frequency will be in this interval. So that's another way to talk about uncertainty. And especially if you take the Y's of the interval, that gives you a natural measurement about your ignorance about this. Okay? You can say, oh, in the near future, that my future frequency will be between 0 and 1. Well, of course, you can say that's always the case because that's where it's defined. Okay? But if you say that, it basically means you don't know. On the other hand, if this two actually convert to one single point, you see that's actually probability in the traditional. So this can be seen as an attempt to extend probability measurement from a single point to by taking future evidence into consideration. So this is the table I have in my book, in which I relate all the measurements I mentioned. Actually, there are 9 of them altogether, or no, 8 of them. Okay, and here I have 7 of them listed. I didn't have that W minus because that's just the difference between these two. But this 3 is a group. Frequency confidence is another group. And this interval is a third group plus the Y's of that interval, which can be calculated from them. What I'm showing in this table is these 3 measurements are functionally equivalent to each other, meaning that give you one, you can calculate the other 2 according to the formula I listed here. Or in other words, it means that uncertainty in our system can be understood or interpreted in several different ways. Okay, but they're all related to each other. But no matter what, one conclusion is crucial. You need more than one number. One single number is not enough. Okay. That actually leads to this slide. And I have published several things that at the very beginning of my development of this model. A major issue is how is this related to probability theory, which dominate the measurement of uncertainty to the degree that many people even think that's the only way to measure uncertainty. Okay. First, be very careful when we are talking about probability. There are actually 2 different things. One is we're talking about probability theory as a mathematical theory. And in that sense, it's pretty clear what we mean. Okay, you can find it in any textbook about probability theory and many other places. And the probability theory is governed by 3 axioms. Well, in some textbook, they just say 2 of them. The other one, they mention them as part of the definition, but it doesn't really matter. It just probability is something you assign is a number between 0 and 1. Okay, you assign it to something in an event space, sometimes called the sample space, and for the whole sample space or event space, the probability is 1. Okay, 100% it must be there. And then this is the so-called addition rule. Okay, so if you know the probability of A and B, you know A and B never happen together, then the probability of A or B is just these two numbers add together. Okay, and that's enough to derive everything in probability theory in principle. Okay, very, very powerful. So that's not the issue. The issue is how to relate that to our thinking. That's not the mathematical formula, it's called the interpretation of probability. Okay, what that thing measures as far as our discussion goes. And there is a huge literature, in case you haven't heard about it, you will be surprised, okay? About this one, this topic, there is a large number of different interpretation about it. Okay. And here I only mentioned the three, I think the most common or most relevant one to this discussion. The first one is called, sometimes called objective, sometimes called frequencies test. Okay, that's the one I mentioned, is the limit of relative frequency. That is how often something happens in a long stream of repeatable experiments. Okay, that's the one you learn in your textbook of probability theory and statistics, which is perfect, wonderful, which is the foundation of many important things. But the way you apply it here into human thinking, there are a lot of trouble. Now, the first thing, the most common mentioned one is, and this measurement is only applicable to repeatable experiment. It will not be applied to one-time event. To simplify that example, you cannot really talk about what's the chance or probability for tomorrow to rain. This is not whether you can predict or not, okay? That question itself doesn't make sense. Because tomorrow is one single point. It will either raining or not, okay? Here we're not talking about the matter of degree of raining. It's only when you talk about repeatable experiment, you can talk about the chance for us to run into rain in this region, in this season, because that's repeatable observation. Okay, one-time observation, you don't have probability defined at all. So because of that and many other related issues, there is a second one, it's called subjective, which just say that probability is your degree of belief. That one is more general than this relative frequency limit definition because it can be applied to one-time event. Okay. For example, example often used in the US is who will be the next president of the country. Okay, that's a one-time event. And the different people have different opinion. And that's purely subjective. Okay? You cannot really talk about what is the true probability. That doesn't make sense. So yeah, many people support this, but this one has its own problem because it seems like everything goes. Okay? As far as, I have my opinion, you can have your opinion. You can say there's a 0.8, I can say it's 0.2, and she can say it's 0.5. As soon as you say something is subjective, it seems everything go. Clearly, that's not good for our current business. Then, be careful, even we say subjective interpretation, it still doesn't mean, accurately speaking, everything goes. Because you still need to follow the axioms of probability theory. That's the precondition of all of them. But the subjective interpretation only requires that. That is, as far as you're self-consistent, okay, you can assign any probability to anything. As far as you don't, for example, believe A to 70%, but also believe not A to 60%. That's not allowed because that violates the axiom of probability theory. Other than that, it's your business. So this tool seems too extreme. Many people in AI is taking the third position, which is also related to the Bayesian approach, but not exactly the same thing. So the third position just say that probability is subjective in the sense that different people may have different opinion, but it's not arbitrary because why different people have different opinion? Because they have different evidence. Okay. So probability is a logical relation between your degree of belief and the evidence you have. Very roughly speaking, that's the third position. Okay, you can see that clearly our treatment is closer to the third one, even though still not the same because we don't believe one number will be enough for all the purposes.
Isn't it confusing to even call it probability? Like this feels like you're trying to have some sort of system for keeping track of to what degree, as you said, your evidence and input data fits the model or belief that you have. Why call it even probability?
That is why I never call it probability in
Oh, okay, you
our
don't.
model. Okay, but I have to compare it with probability.
What do you?
But on the other hand, all these people call it probability. In what sense? In the sense that the mathematical model is the same. It's just different people interpret that mathematical model differently. And my approach does not even agree with that mathematical model. So of course, I don't call it probability to avoid confusion, but it's closely related to probability for sure.
Sure. What do you call it?
I just call it truth value.
Truth value, okay.
Or the truth value in my model, of course. So,
well, I think it's kind of unfair to say that probability is just one value because normally you're not talking about probability per se, but you're talking about these distributions which are parameterized by lots of numbers.
yeah.
And if you were talking to us
Yeah.
as a probability person or machine learning person, they'd probably say, oh, your truth value is just a distribution parameterized by two values.
You're right.
So it's the same thing that
If we want to be accurate, okay, of course, probability in that situation is not one number, is a whole distribution. Yeah. But here I'm talking about one specific situation, that is, what is the probability for example, for a certain variable to take a certain value in a given situation. So even if you say, you can still say, or even that is a probability distribution. But no matter what, eventually when you're making decisions, you have, for example, you have to calculate the expected value. Okay?
Right.
Otherwise, you cannot, for example, make your decision or make a bet or whatever. So there is a lot of discussion. Basically, the idea is no matter what you have, you can even say, I don't even have one single distribution. I have a whole bunch of distributions which need to be combined. But eventually, it will end up with one number. Because later we'll discuss that. Because that's required when you compare different options. You cannot directly compare two distribution functions to say which one is better. Eventually, it end up saying, okay, your chance is 0.5, my chance is 0.7, so you should go this way. Okay, so many decisions eventually end up with the comparison of a single number. And that now the question is whether, well, then you can ask, oh, you have the same issue if you use two numbers. Later we'll see, they have the same issue. But still, there is a key difference. That is, at least I can say, my two numbers does not follow probability axioms. You cannot derive from the axioms.
Yes.
Then it go back to this point. Why do you want to follow probability theory in the first place? Just because there is a book already available? Of course, it's not that simple. Okay, it's not simple. There are all bunch of argument which argue for the normativity of probability theory, meaning that you have to follow it. Otherwise, you're in trouble. Okay? One of the best example is the so-called Dutch book example, say that if your beliefs does not agree with probability, especially if it's not consistent in the probability sense, you will run into problem in your decision making, which we don't have the time for details. There is another criticism to probability models. This is from psychology. Okay. There is a huge literature. You may have heard about it. And the best known work is by psychologists Tversky and Kahneman. And Kahneman actually got a Nobel Prize related to this work, starting from the 70s of last century. They systematically shows human decision-making in real life does not follow probability. This is well documented. But the problem is how to interpret that. The typical interpretation is to call it human bias or fallacy. Just basically say probability model is right, humans are wrong, because we're not that good at math, right? So we make mistakes. But my position actually is very different. I'm arguing humans in many situations, it's documented here, are actually right. The problem is the probabilistic model is too narrow. It doesn't really capture the situation which people are actually running into in daily. So we do have a reason to violate probability. And this is a paper I published in 2004 in the Journal of Artificial Intelligence, which I gave a detailed explanation about. I'm not saying that the Bayesian learning approach is wrong. What I'm saying is limited. Okay, there's something that it cannot handle. So we need new model to handle those situations. And that's what I'm trying. This, in a sense, is also not completely new because in the field of uncertain reasoning in AI, there are a lot of people actually start from the 80s or even earlier than that, criticize the probabilistic approach. Basically, the idea is this: probability allow you to handle uncertainty. Say that whether it will rain or not, I don't know. Is a random number is captured by probability, but they somehow assume they know the probability or they know the distribution or they assume there is a distribution to be discovered. The problem is many people, including me, think even that you don't know. Okay, so based on this similar ideas, there are all bunch of approach. For example, people talk about second order probability. The probability value itself is uncertain. So how about, then people say, how about third order and the fourth order? So you get infinite regression, right? And also there is a bunch of people, there are also several books on the so-called impressionist probability, which is similar to my representation of using an interval rather than a point to represent your degree of belief. Okay, you're very often, if you ask people, what's your opinion about the probability of this thing? People say, I cannot be that accurate, but I think it's, say, like between 80% to 90%. And many people will do that. So some people try to build a mathematical model based on that. But that's also somehow related to my work, but not exactly the same. And also, you see here, it's important to realize that accuracy is not really the important issue. Very often, say like in natural language, we usually use words to describe different levels of uncertainty. We say very likely, extremely likely. We don't say 0.7, 0.8, or 0.75. This is actually a major reason why AI, for a long time, does not really like numerical measurement until, say, the 80s, until the Bayesian network became popular. And before that, John McCarthy explicitly say that where are the numbers come from? Okay, it's kind of like arbitrary. So they still prefer to use binary logic for a reason. But now we have, at least in my model, there is a way to use non-numerical representation. The basic idea is to allow different level of uncertainty, both in frequency and in confidence. So a larger interval means that I'm not that accurate. We can do that. And also inconsistency. You see that the people who believe a probability is good, again, go back to this Dutch box thing. At least you need to be self-consistent, which I always say that, yes, I hope I'm self-consistent. But very often, especially given the restriction I put before, insufficient knowledge and resource, very often you simply cannot get it. It's not because you don't want it. Okay? We are not self-consistent. We are not. We have conflicts in our mind on many things. Okay? Sometimes I think, yeah, this is good. Sometimes no, but the same thing I think is not that good. Okay? You cannot completely get rid of those things, again, because of this AIKR restriction. So first, I say it's inevitable. Some kind of inconsistency have to be tolerated. Second one is also important. I think it's manageable. In our system, we allow inconsistency, but it will not kill the system, will not make the system crash. Like in traditional many models, they don't allow it because they don't know how to deal with it. And as soon as you have inconsistency, basically it crashes. So that's it. So there's the readings, at least some other people's work and also my work. So today is basically about semantics, about knowledge representation. Okay. So next week we will actually go in. So I'm consistently take 10 more minutes of the lecture time. But since we don't have such a big group, I think we're flexible. So let's take a break for 10 minutes, then we can still have some good discussion. Okay.